Hola, en particular para mí, buenos días. Bienvenidos a este primer coloquio de IPARCOS del ciclo 24-25. Antes de presentar otra vez a nuestro speaker, quería también anunciaros que para el día 28 de noviembre, o sea, dentro de un mes, tendremos el siguiente coloquio. Esta vez será impartido por Roberto Emparán de la Universidad de Ciencias del Instituto de Ciencias del Cosmos de la Universidad de Barcelona y nos va a hablar de radiación de Hawking. En particular, el título es algo así como La luz que viene de la oscuridad, medio siglo de radiación de agujeros negros. Esto, como digo, será el 28 de noviembre. Hoy tenemos aquí a Shane O'Sullivan y como la charla va a ser en inglés, pues si no os importa voy a pasar directamente a inglés. And today we have the speaker, which is Shane O'Sullivan from IPARCOS and from the Department of Astrophysics. He did his PhD thesis in 2010, right, in University College at Cork, Ireland, and then, in radio astronomy, as you will see probably. And then he was as a postdoc in Sydney and had different positions throughout the world, in particular in Mexico, Germany, Ireland again, until last year he joined IPARCOS with an Atracción de Talento within that program, and so I hope we will have him here for quite a few years. And I think that's it. The title, you've got it there, Illuminating the Universe with Cosmic Magnetic Fields, and I think it's better that we listen to him than to me, so please, Shane.
Thanks very much, Luis, for the very nice introduction and for giving me the opportunity to speak to you today about my research in recent years on trying to measure magnetic fields in intergalactic space. Okay, so I'm sure you all know that and appreciate that magnetic fields are very important for lots of different astrophysical processes, or many processes throughout the universe. Such as protecting us, the Earth's magnetic field protects us from the harmful radiation from the sun. So it's important for the development of life on planets, on exoplanets, as well as our own planet. Magnetic fields have an important role to play in star formation in the universe. So they kind of modulate the collapse of molecular clouds and the production of stars. They also can do quite extreme things like extract energy from spinning supermassive black holes, and more mundane things but also quite useful things like attaching things to your refrigerator at home. So there's many different scales of magnetic field in lots of different objects. So we know that planets have magnetic fields, stars have magnetic fields. Strong ordered magnetic fields is what I mean, and even on galactic scales we have large-scale ordered magnetic fields in spiral galaxies, which is sometimes something of a surprise, as well as in the intergalactic or the intercluster medium, say between galaxies in very dense environments. But the properties of these magnetic fields are all very well studied these days, so they have direct measurements. But what's less studied are magnetic fields on the largest scales in the universe. So in what we call these cosmic web filaments and voids of the universe. But the range of magnetic field strengths in the universe is quite impressive. So we think it's about of order 10 to the 30 orders of magnitude in field strength. So the Earth sits somewhere in the middle here with about a Gauss magnetic field strength at the surface, a little bit less. Apologies for non-SI units, but I'll be talking exclusively about Gauss, but you can write down or convert in your mind now if you're more familiar with Teslas. 1 Gauss is 10 to the minus 4 Teslas. But the largest magnetic field strengths in the universe are associated with these stellar remnants, neutron stars, and so these can be as large as 10 to the 15 Gauss. So this is much, much larger than the strongest magnetic fields that can be created on labs in Earth. And so stars then, like the sun, so have of order a Gauss or up to kilogauss magnetic field strengths. And then as we extend into the interstellar medium of galaxies, you can have magnetic field strengths of order microgauss. And similarly in galaxy clusters, so in the hot ionized gas in between galaxies and galaxy clusters, we have several measurements of magnetic field strengths of order a microgauss as well. But so we're trying to push even further into more diffuse and weakly magnetized regions of the universe. And in the last couple of decades, we found that actually even on the largest scales in the universe, in these cosmic voids where there's very little matter. If you're not familiar with the cosmic web of structure, so we have this pattern in the large-scale structure of the universe where you have these overdense regions of matter called nodes. You have regions, highly underdense regions with very little matter and galaxies called voids, and then you have these connecting regions called filaments. And so this is what we call the cosmic web, and I'll talk a lot about cosmic web filaments and cosmic voids at the start. Okay, and so recently we've had some limits placed on the strength of magnetic field in these void regions, ranging from somewhere between 10 to the minus 16 Gauss and 1 nanogauss. And so it's quite surprising to have measured large-scale magnetic fields in these very low density and kind of semi-empty regions of space. And so a natural question is, where did these magnetic fields come from? Okay, so we call this, the problem that we want to answer is the origin of magnetic fields, or magnetogenesis. And so there's kind of two broad classes of models here. One is where you have large scale or magnetic fields produced, let's say volume-filling magnetic fields produced in the very early universe, and we call these primordial magnetic fields. So these are formed before stars and galaxies. And so then these initial magnetic fields will then evolve with the structure formation throughout the history of the universe. And so these magnetic fields have then a particular pattern that's very closely matched to the actual cosmic web pattern, because the fields are diluted in cosmic voids, they're compressed and enhanced in cosmic filaments, and similarly in nodes, then they're strongly amplified by all the turbulent gas motions in these regions of the universe. And so the magnetic field strength then in simulations from a primordial scenario has this nice pattern that kind of reflects the underlying matter distribution in the universe. But then the alternative is that there were no magnetic fields, or not very strong magnetic fields, or not very strong primordial magnetic fields, but instead magnetic fields were first produced on very small scales due to some sort of plasma instabilities or other mechanisms, and then they're amplified in stars and galaxies and then expelled out into the intergalactic medium. And so this is where you have fields created on small scales at later times, and then they're kind of polluting the universe from AGN jets and galactic outflows. But now this astrophysical scenario has a very different pattern on the larger scales. So now the magnetic fields are strongly amplified in these overdense regions where they're first produced, but then they do not fill the volume as much as the primordial fields. So they cannot travel so far into these cosmic web filaments and voids. And so the magnetic field strength in these regions is either, in this astrophysical scenario, is either non-existent or very, very weak. And so this is why we are very interested in measuring magnetic field strengths in filaments and voids, because then we can try to distinguish between these two scenarios. And of course, potentially both are occurring. So if you have primordial fields, then you almost certainly have these astrophysical scenarios as well, where you're getting fields ejected out into the universe. Okay, and so what do we know currently about the strength of magnetic fields in these filaments and voids? Particularly in voids, we have upper limits from the cosmic microwave background radiation. So if you have strong magnetic fields in the primordial universe, this will create extra clumping of material, of baryons, and so this will actually affect the temperature anisotropies in the cosmic microwave background radiation. And so if there are strong magnetic fields in the early universe, it will produce these non-Gaussian fluctuations in the CMB. And so from the detection or the non-detection of non-Gaussian fluctuations in the CMB, you can place an upper limit on the magnetic field strengths of a few nanogauss. But then excitingly from the other side, so putting lower limits, so about 20 years ago, there was lower limits placed on magnetic fields in voids. So this then says that, okay, there are significant magnetic fields in voids if you believe this work, and so it has been tested a lot in the last 20 years, and we're now relatively confident that this is a real effect where you have very high energy gamma rays propagating through cosmic voids and giving us a limit on the magnetic fields in these voids of about 10 to the minus 7 nanogauss. So magnetic fields greater than 10 to the minus 16 Gauss. And so this effect is, okay, well, first of all, these very high energy tera electron volt gamma rays are produced in plasma jets emanating from supermassive black holes, or powered by supermassive black holes. And so these tera electron volt gamma rays have very long mean free paths, so they can escape the immediate region in which they were formed, and they can propagate freely through the intergalactic medium until they encounter a photon of light. This is, well, the extragalactic background light, so it's just the light from all the stars and galaxies that is propagating through the universe. And so when the gamma ray interacts with this photon, it produces a pair, or an electron-positron pair, and now you have a charged particle propagating through these voids, and so in the presence of a magnetic field, these charged particles get deflected. And so then these deflected charged particles can then produce gamma rays again, lower energy gamma rays by colliding with cosmic ray or the CMB photons. And so the prediction is that if you have no magnetic fields, then these secondary lower energy gamma rays should be detected at a later time than this initial tera electron volt signal. And so the absence of this secondary gamma ray photon gives us this limit on the magnetic field strength. And so this is called the suppression of this secondary lower energy gamma ray cascade. And so from the previous slide, I showed you that we have this different behavior of the strength of the magnetic field with cosmic overdensity. And so then we can use this measurement in cosmic voids to give us an idea of what scenario is preferred. And so this is a crude plot then of the magnetic field strength as a function of cosmic overdensity. So if you have very overdense regions like galaxies and clusters, we have very nice measurements from radio telescopes in these environments, and we find of order 1 microgauss in these regions. I will talk mainly for the rest of the talk about trying to measure magnetic field strength in filaments, but the limits we have already from these gamma ray measurements and the cosmic microwave background really do favor this primordial scenario, where you have significant volume filling fields in void regions of the universe. Okay, and so why then is it so interesting to actually determine whether primordial magnetic fields existed or not? And so the key here is that potentially they provide us with a very unique window into physics of the very early universe, which we cannot otherwise probe. And so, from the history of the universe, we can use photons to probe, the properties of the universe back to about 400,000 years after the Big Bang. So before that, the universe is opaque to photons, so we need other means to actually to understand what's going on in the very early universe. So from Big Bang nucleosynthesis, we have the estimate of the abundance of elements. So this gives us a window into about 3 minutes after the Big Bang. There's also this cosmic neutrino background, that was produced maybe about a second after the Big Bang. But this will be very, very difficult to measure. So neutrinos are already, high energy neutrinos are already difficult to measure, and these lower energy ones are even more difficult. Okay, but then the key point here is that we want to use, if these magnetic fields are produced in the very early universe, then it gives us an actual window into the universe about a microsecond or so after the Big Bang. And so there's several models for the production of these primordial magnetic fields. So they can be produced during inflation, or they can be produced during phase transitions in the early universe associated with the electroweak phase transition, or the color confinement, the production of protons and neutrons in the universe. And so this is quite interesting to give us this window on the very early universe. And also in these phase transition models, the productions of these magnetic fields is associated with the production of gravitational waves, because you have disturbances in the very early universe material or fields that also produce gravitational waves. And so there was a potential detection of a gravitational wave background that could be associated with these very early universe phase transitions, or it could be related to supermassive black holes in our universe. And so the additional information provided by magnetic fields might help us to better understand this epoch of the universe. Okay, and then magnetic fields might also be related to the asymmetry of matter, why we have more matter than antimatter, and also these dark matter candidate particles known as axions have a very weak, or a proposed weak coupling with the electromagnetic field, so they might also be associated with the production of magnetic fields in the early universe. Okay, and then at slightly later times, so not in this primordial universe within a microsecond, we also have this problem you might have heard of this kind of disagreement between different ways of measuring the Hubble constant. So if we measure the Hubble constant from the cosmic microwave background, we get a value of about 67 kilometers per second per megaparsec. But if we measure it using supernova in the later universe, we get a value of about 73 kilometers per second per megaparsec. And actually the existence of strong magnetic fields in the early universe can actually affect some of the assumptions that go into the cosmic microwave background calculations that produce this value of 67 for the Hubble constant. And so if you have primordial magnetic fields of a particular strength, these create additional baryon clumping, or clumping of material in the early universe, such that recombination actually happens slightly earlier. And so if recombination happens slightly earlier, you have a slightly smaller sound horizon, or a slightly smaller distance to recombination. And so distances are inversely proportional to the Hubble constant. So if you have an earlier recombination, then this increases the value of the Hubble constant. And so with these magnetic field strengths, we can potentially alleviate, so it doesn't immediately solve this Hubble tension. So you get something closer to 73 kilometers per second per megaparsec, but not quite. Oh, sorry. And then finally, just on the influences on potential structure formation in the early universe, this additional baryon clumping that these magnetic fields can produce can also be related to galaxy and early star and galaxy formation. And so then you can have slightly earlier formation of small structures like dwarf galaxies that can affect the ionization history of the universe. And so you get this little bump in the power spectrum of the matter in the universe on these small scales due to these primordial fields. And well, a speculation on my part is that these might help, explain some of these kind of earlier than expected galaxy formation that we're being told about from these James Webb observations. Okay, so that's a way of introduction. For the rest of the talk, I will focus solely on radio telescope observations and what they tell us about cosmic magnetic fields, particularly in filaments. And so, yeah, these radio telescopes are excellent tracers of magnetic fields in the universe, mainly due to two physical processes. One is synchrotron radiation and the other is Faraday rotation, and these are interlinked. So this is a nice picture of a radio galaxy where orange depicts the radio emission and the white emission is the light from the stars in the host galaxy. So there's a supermassive black hole at the center of this galaxy. It's powering plasma jets that are magnetized and have electrons, and these are producing this synchrotron emission. So when you have a relativistic electron spiraling around a magnetic field line, it produces synchrotron radiation. But the preferred orientation of the spiraling of the electron compared to the magnetic field also produces polarization of the synchrotron radiation. So synchrotron radiation is highly linearly polarized. So you have this preference perpendicular to the magnetic field for the oscillation of the electron, which generates this linearly polarized light. And then we have a whole population of these relativistic electrons in these plasma bubbles, and we have slightly more, or a lot more lower energy relativistic electrons than higher energy ones. So this leads to a power law distribution in the intensity of the synchrotron radiation as a function of frequency. And so this means that at lower frequencies, the synchrotron radiation is brighter, and so then it's easier to detect at radio wavelengths. And this traces mainly the perpendicular component of the field on the plane of the sky. Whereas the other phenomena of Faraday rotation is due to the actual rotation of the linear polarized synchrotron radiation as it passes through a cloud of magnetized and ionized gas. So this Faraday effect was discovered by Michael Faraday in about 1845, and so it tells us about the free electron density in the gas, as well as the line of sight magnetic field along a particular path length of the region of ionized gas. And so this is just a depiction of the same radio galaxy, but now the color tells you the Faraday rotation fluctuations that you see quite close to the radio source due to the thermal and magnetized material close to this radio galaxy. Okay, and just to go into a bit more detail about Faraday rotation, because the rest of the talk is focused on Faraday rotation. So you have this source of linearly polarized light, so these radio galaxies. And so this linearly polarized light then propagates through magnetized and ionized gas as it propagates through the universe to us. And so it has an initial amplitude, this electromagnetic or polarized electromagnetic wave, and a particular polarization angle. And so then this polarization angle is modified from its intrinsic value, this chi0, so when it was emitted, and it's modified by this Faraday rotation as a function of the wavelength squared. And so then all we have to do is measure the actual polarization angle as a function of wavelength squared to determine the amplitude or the magnitude of this Faraday rotation effect. And so this rotation measure is the integral of basically all the clouds of magnetized and ionized gas along the line of sight. And so it tells us about the gas density as well as the magnetic field. Right, and because it's due to the line of sight, you can have positive or negative Faraday rotation measure values. Okay, and in even more detail, so we have many contributions. So this is the advantage, but also a disadvantage of using Faraday rotation is it's the accumulation of all the material, all the magnetized, ionized gas along the line of sight. So there's many contributions on many different scales. So you have the radio galaxy, but then it's embedded. So the green here is the synchrotron emission, radio emission, and then the purple and blue is X-ray, so hot ionized gas surrounding the radio galaxy. And this, we know that this hot ionized gas is also magnetized. And so this produces quite a large Faraday rotation effect, very local to the radio source. Okay, but then the radiation passes through this region, but then it also passes through the interstellar medium of our galaxy, which I told you is magnetized. And so this also produces Faraday rotation, as well as our ionosphere. And this is our telescope. So we need to account for the rotation measure from our Milky Way, as well as the ionosphere. So we can measure the ionosphere directly, so that's not a big problem. Then we have galaxies that could intervene along the line of sight. So you just have a random galaxy, and it will have some Faraday rotation contribution due to the magnetic fields and gas. And then what we're really interested in is the actual, well, at least in this case, is the magnetic fields associated with the cosmic web filaments in the large-scale structure. Okay, so our optical colleagues are very good at measuring where or determining where all the galaxies are in the universe. So if we don't want to study galaxies, we can easily remove the lines of sight that have galaxies. So this makes our job a lot easier. Then we also put a lot of effort into developing models of the Faraday rotation from just the Milky Way alone. And so if we have a good enough model, then we can subtract this Faraday rotation from the Milky Way as well. And the ionosphere, I said, yeah, we can measure this directly, so we have good measurements every 15 minutes or so for the ionosphere. So then we're left mainly with this intergalactic component, which is very small, and a local component, which causes us lots of headaches. Okay, so if we want to measure this intergalactic magnetic field, then what's the magnitude of this effect in this rotation measure quantity? So we can have a particular cosmic web filament over density, so of about 50, so compared to the average density of the universe. This leads to a particular particle number density of electrons. And then if we pick a particular line of sight through a filament with, say, a strong magnetic field of 100 nanogauss, then we'd end up with something of order of 1 radian per meter squared. So yeah, we're not very good with units in astronomy. Radians per meter squared, and then we have other units on the other side, but yeah, not to worry. But so 1 radian per meter squared rotates this linear polarization angle by about 2 degrees at centimeter wavelengths. But then if you go to meter wavelengths, it rotates it by 200 degrees. So you can see that the effect of small amounts of Faraday rotation is much easier to measure at longer wavelengths. And so the effect or the result of this is that we can actually measure the Faraday rotation with much higher precision at these meter wavelengths. And so this is why most of my talk I'll be talking about the low frequency array, which is a radio interferometer at meter wavelengths. And so we can measure this Faraday rotation with about 100 times better precision than at centimeter wavelengths. And so if we want to measure 1 radian per meter squared, then yeah, it's good to have the uncertainty in our measurements much lower than this. Okay, and so this LOFAR telescope is a pretty amazing array, basically, of sensors, so just pieces of wire on the ground that are sensitive to meter wavelength radiation. And it operates, from about 30 meters to 1.25 meters. And because it's a radio interferometer, you can combine the signals from all these different locations throughout Europe to actually achieve an angular resolution that's comparable to the resolution at optical wavelengths, because the angular resolution of a telescope is proportional to the wavelength that you're observing at divided by the size of your aperture. And so the effective size of the aperture when you combine all the signals from this interferometer is about 2,000 kilometers. So it's like having a telescope of 2,000 kilometers, not quite the same sensitivity as a telescope that size, but with the resolution of a telescope that size. And so we can achieve up to 0.3 arcsecond angular resolution. We have problems producing these images because it takes a lot of computing power. So for the most of the talk, I'll be talking about slightly lower angular resolution observations. So LOFAR is also super sensitive telescope, and so recently it discovered a very large radio galaxy. So a radio galaxy that's about 7 megaparsecs in size. So this is pretty crazy, over 100 times the size of the Milky Way. The data that I will talk about is from this LOFAR telescope, and in particular, an all-sky or a northern hemisphere survey at 2 meters wavelength roughly. And so we have relatively low angular resolution, but that's so we can process the data a little bit faster. This low-FAR survey, this just means it's a very sensitive survey compared to other radio surveys. We had a public data release last year, which covered about 27% of the northern sky. And so that's the data I'll talk about. So about 5,700 square degrees. Over 4 million radio sources. Unfortunately, not as many polarized radio sources. So we only detect about 0.2% of the total sources in polarization. But thankfully it's more than 0%. So we actually we can actually do useful science with this number of sources because of the exceptional precision with which we measure the Faraday rotation. Okay, the survey continues, and hopefully by early next year we'll have most of the northern sky covered. Okay, but the last few years of my life we're trying to create this plot. So trying to measure or find the linearly polarized sources and measure their Faraday rotation. And so what I've now done is turn this beautiful radio galaxy into just a single little circle. And so each of these circles correspond to the Faraday rotation measured towards this radio galaxy. And the size of the circle corresponds to the magnitude of the effect, and the color is just the average line of sight magnetic field in that location. Okay, but so what we want to, for this particular study, we want to actually study the extragalactic Faraday rotation. So we use our model of the galactic Faraday rotation and subtract it from the observed rotation measure to end up with the residual rotation measure. So now you see that these large-scale patterns that are indicative of large-scale magnetic fields quite close to us in the Milky Way, this goes away and we're left with this random pattern. And so, in histograms, this looks like this, where you go from the rotation measure, which has a non-zero mean, because it's this local, large-scale, correlated regions, and then we subtract this model, and we end up with a distribution that's centered on 0, but has this particular spread. And so this is very important for the rest of the talk, because this spread, so the spread is more narrow if you're probing regions of low magnetic field and low particle density. And it would be very broad if you probed a region of high magnetic field strength and high density. Because this is many lines of sight, through different regions, and so, this is how we measure or quantify the amount of Faraday rotation in the extragalactic universe. We use this estimate of the dispersion. Okay, and so then to try and measure the magnetic field strength in these filaments, we use the measurement of this dispersion, but in different redshift bins. So we say, okay, all of the Faraday rotation measurements that come from radio galaxies less than a redshift of 0.5, we get the dispersion of those, and we plot them. And then we do this for many different redshift bins. And what I'm showing here is not that, but it's the actual number of optically identified filaments along the line of sight. So our optical colleagues do these very nice galaxy surveys so we can say where these matter structures are along the line of sight. And then from simulations, we expect this dispersion in the Faraday rotation to actually increase depending on the number of filaments that it crosses. So if you have a high redshift radio galaxy, the light from it crosses many cosmic web filaments along the line of sight. And so then we parameterize it with this very simple equation which describes how the dispersion in this Faraday rotation will increase as a function of redshift, or as a function of the number of filaments it's crossing. And so then we can fit, so the blue points here are the observed data points, we can fit this simple model then to get an estimate of the typical dispersion from an individual or a single filament. And this comes out at about 0.7 radians per meter squared. And so then this is the convolution of the particle density or the product of the particle density and the magnetic field. So we always have to make some assumptions or have some alternative measurements of the particle density distribution to actually get the magnetic field. But we can have, back of the envelope type calculations that tells us, okay, this is of order of tens of nanogauss. We do much more detailed modeling where we will use semi-analytic models as well as cosmological MHD simulations to actually try to estimate the magnetic field strengths that produce this sort of signal. And so we still get of order 10 to 40 nanogauss in the local universe for these measurements. Okay, so now on the earlier plot that I showed you, where does 30 nanogauss or 10 nanogauss fit? And so in our filaments now, we have this proposed measurement of about 10 nanogauss at these cosmic overdensities. So again, this seems to favor these primordial scenarios where you would not expect the outflows from galaxies and AGN to actually fill the volume of these filaments. Okay, but it's not just Faraday rotation, so we have other tracers, or well, at least other experiments to measure or try to determine the magnetic fields in these filaments. And one is through stacking loads of filaments together in radio maps, which I won't explain in any detail, but it's trying to probe the synchrotron emission that's actually produced in shocks onto these cosmic web filaments. So you have shocks producing relativistic electrons that then illuminate the magnetic fields that are in these cosmic web filaments. And so you have also the polarized light from these filaments. And so this also, from these measurements, we also have estimates of magnetic field strength in these filaments of order 10 to 40 nanogauss. We can also do different experiments with the Faraday rotation, and we also get consistent results. Okay, but now coming back to probing the first microsecond of the universe, can we actually use these measurements of magnetic fields in effectively the late universe to actually tell us something about the very early universe? And also, distinguish between these primordial and astrophysical scenarios. And so to do this, we use cosmological MHD simulations, and many ones that have different initial conditions for the magnetic fields in the universe. Right, and so that's what's shown here. So this is what's called a magnetic field power spectrum. So, and you have these different slopes. So what it means is that on these small k values, you have, on large scales, you have a lot of magnetic energy, and on smaller scales, you have less magnetic energy. And so there's different sort of scenarios. So if the magnetic fields are produced during inflation, we expect to have more magnetic energy on larger scales, whereas if they're produced during these phase transitions much later, we expect the fields to have more magnetic energy on the smaller scales. And we constrain these actual input power spectrum by the cosmic wave microwave background, so that we can't have normalizations that are higher than allowed by the cosmic microwave background. And so then we want to compare this with our data. And so there's two things on this plot. One, again, is this dispersion in the Faraday rotation. So the observed data points are in black here. So we have subtracted what we believe are local contributions to radio galaxies, and we're left with what we assume is mainly from cosmic web filaments. Now we have these large oscillations which are not present in the actual simulations. So these are either telling us something about the universe or they're statistical fluctuations, because we only have, say, 30 or 40 data points in each of these bins. In future we want to increase the number of data points in each of these bins so that hopefully these fluctuations either go away or become more statistically significant. But then the gray line, or gray data points, are a kind of the same experiment but using cosmological MHD simulations. And so these gray data points are from a simulation where you just put in a uniform volume-filling magnetic field of strength 0.1 nanogauss. And so what this tells us is that the simulations, the values at the highest redshifts, so around redshift 2, these predict much higher Faraday rotation than is observed. And so then we say we have ruled out primordial uniform magnetic fields, so magnetic fields with scale lengths the size of the universe that would be produced, say, very early on in inflation. How they survive, I have no idea. But we can say that if they survive at this strength, this is inconsistent with the data. Then we can use these power spectra, so looking at this tilt of -1, so more magnetic energy on larger scales. We have a particular prediction for the Faraday rotation from these magnetic fields. And so these blue data points track much more closely to the observed data points. And so these are consistent with these kind of stochastic primordial magnetic fields with an amplitude on megaparsec scales of about 0.4 nanogauss. So these are the most consistent, say, levels of magnetic field strength with the current data. And this is the more kind of inflationary type scenario. So these astrophysical scenarios, which we have already ruled out, so these are quite consistent with the data in the local universe because these magnetic bubbles and AGN jets have had enough time to expand and pollute more of the local universe. And so we can get models that are consistent with the local universe, but they haven't had enough time to expand in the early universe, and so these are highly inconsistent with the data at the highest redshift end. Okay, but we can combine the astrophysical and the primordial, which is nice because we believe probably both of these things are actually occurring. And this provides a slightly better, description of the data in the lowest redshift end. Okay, and then the final point here is that it's quite exciting that we can actually say that these causal mechanisms, I put causal in inverted commas because I should just say, magnetic fields primordial magnetic fields that have a lot of energy on small scales. So we can actually rule these out as unlikely because the inputs are consistent with the maximum allowed by the cosmic microwave background, but then the output in terms of the Faraday rotation, is much lower than the actual observations. And so we cannot increase the normalization of the field to actually reproduce the Faraday rotation data without violating the CMB constraints. So then we can say that these causal type scenarios are disfavored. Okay, so that's the main point or conclusion that I wanted to get to in the talk. In the last few minutes, I wanted to kind of focus a little bit more on the actual, measuring the gas flows in the large-scale structure. So it's also interesting to actually measure the properties of gas and how they extend beyond the halos of galaxies, because most of the material in the universe, so most of the normal matter even, does not exist within galaxies, like stars or galaxies. It's just, and the local universe is just ionized material floating through intergalactic space. And so, we call or refer to this as kind of the missing baryon problem, where we can find and observe all of the normal matter very easily in stars and galaxies because they're very bright. But then we have all of this kind of tenuous gas, low temperature or kind of mid-temperature gas floating through the universe that's very difficult to observe. And so from simulations, again, we have an idea of what should be there. So this is an example of the temperature within like 500 kiloparsecs around a group of galaxies. This is the gas density. So these are predictions of what should be there. But then what we typically observe, with our X-ray telescope, which is very good for detecting hot gas, so about 10 to the 8 Kelvin, from X-rays, we see, a portion of this gas. Okay, but then it can be quite, you have to go to quite a large radius to actually, to find all of the baryons that kind of are predicted to be there from our understanding of the early universe. So on how many, what the universal baryon fraction is. Oops. Is this play? Oh, okay. So, but then because we have so few observations in these extended regions beyond galaxies, different cosmological simulations actually predict very different things. So what's being shown here is the gas density in blue and the gas temperature in red or orange. And this is about 25 megaparsecs on a side. So all of these different amazing simulations actually produce slightly different, well in this case very different, distributions of the gas on large scales. And but they all produce the galaxy properties perfectly. So they all produce, how many stars we have in galaxies and galaxies of certain mass. So they're all very well matched to, the best observations, but then we don't have very good observations to actually constrain these simulations on these larger scales. And so this is where hopefully Faraday rotation will help. And this is an example then not of a meter wavelength rotation measure grid, but an actual centimeter wavelength rotation measure grid that we've just started to construct. So we have about 200,000 RMs, so many, many more than the meter wavelength one, but less actual precision in the individual values. But it's quite good for probing these kind of more dense regions of the universe. Okay, and so this is an ongoing survey that'll go for the next 4 or 5 years, and we have about 20% of the sky. So there are, like every little dot here is actually a Faraday rotation measure value, but there's so many dots, it looks almost like a continuous kind of map within these tiles. Okay, and some early results from this survey is again detecting the dispersion in the Faraday rotation associated with these astrophysical structures. So this is an example of the simulation. And so what we did was we studied like 55 nearby groups. So again, we're giving a statistical measurement of the gas in the halos of nearby groups. And so we're plotting this dispersion as a function of the radius from the centers of these groups. And so we have these lines of sight, basically, about 12 lines of sight through, all of these 55 nearby galaxies, so that we have an idea of the distribution of gas. And so what we're finding is that, within the virial radii, so this 500 kiloparsec region, we find an excess in the dispersion, which we associate to this, this hot, denser gas, within the virial radius of this group. And then we also see an excess over this extragalactic background. So if we point randomly anywhere in the sky and average up all those signals, we get of order 6 radians per meter squared. So if we're not pointing through galaxy groups, or not observing the lines of sight through galaxy groups, we see this, we should see this sort of level. But we see an excess related potentially, on these two different scales. And the second scale here, this warm, hot intergalactic medium, means gas of like 10 to the 4 to 10 to the 6 Kelvin, and very tenuous gas that's the filaments that are feeding onto this galaxy group. Okay, and we have estimates then of the magnetic field strengths as well, which is less the emphasis in this particular part of the talk. Okay, and then finally, we're also looking at the gas in between galaxy clusters, and in particular matter bridges between massive clusters. So in these clusters, we have good measurements of the actual gas densities, and so this can give us better constraints on the actual magnetic field. But this particular example here is of the center of the Shapley supercluster. So it's one of the most massive clusters in the universe. And this is work done by David Alonso Lopez, a PhD student here at the Complutense. And so this contour outlines the gas density associated with these clusters, and the triangles are the Faraday rotation lines of sight that we have through this region. And so this allows us to then study the gas and magnetic field properties of these matter bridges that are kind of connecting these filaments. So you see that there's lots of gas in this region, but with stars and galaxies, we're only probing a very small part of this larger matter structure. And so we can probe these potentially, missing baryons in these superclusters with this Faraday rotation effect. And so again, David finds of order microgauss magnetic fields even in these regions in between the galaxy clusters. Okay, so that's pretty much the extent of the talk. Just to mention a little bit about the future. Already, currently, it's super exciting in the field because we actually have lots of new data from new telescopes. But a lot of this has been a prelude to this square kilometer array, which is this next generation radio telescope. And it's actually two telescopes. So there's one at centimeter wavelengths and one at meter wavelengths. One is in Australia, one is in South Africa. So the South African one is here, and this is just a composite, and the Australian one is here. And yeah, just to mention, Spain is a full member of the SKA, so we have access to all the amazing data that the SKA will produce in the 2030s. So a little bit to wait, but we have lots of data currently. And yeah, the SKA is not just for measuring Faraday rotation. Okay, there is the best working group is here, the magnetism one. But there are also many other ones where if you observe these pulsars, so these radio emitting stars, you can constrain gravitational waves. We can also detect high-energy cosmic ray particles that interact with our atmosphere in radio waves. Much of radio astronomy was driven by this detections of the hydrogen spectral line. And so this gives us an insight into all the hydrogen in the universe, which most of the universe is just hydrogen. And many other things studying the sun, obviously very strong magnetic field and activity on the sun. Okay, and the construction has already started, but there's a bit of work to do. So particularly for the SK low, they have to put 130,000 antennas across about 74 kilometers. So these antennas are like kind of wire Christmas trees. And then the more traditional dish telescopes, about 100 or close to 200 of those in South Africa. And so this will achieve resolution comparable to optical telescopes with amazing sensitivity, whereas these have slightly lower resolution, but have the unique advantage, or some unique advantages. Okay, and the SKA is always open to new members and new science cases, so nothing is fixed in stone in terms of what they're going to observe or how they're going to observe, so they're always interested in new ideas. Okay, so then just to summarize, so both radio and gamma ray observations really favor these primordial magnetic field scenarios. And this is very interesting because these primordial fields actually give us a window into the first microseconds of the universe. And then we have some limits on the actual magnetic field strength from radio observations that are about 10 times better than what we get from these cosmic microwave background experiments. So this makes me feel quite useful in this area. And so also this Faraday rotation is becoming quite a unique probe of these very extended regions of magnetized gas surrounding galaxies, and the matter flows that are flowing out of galaxies and into galaxies, kind of determining the evolution of galaxies on the largest scales. Okay, and then, current future or near future is very bright, and the slightly more distant future is also very bright with this SKA on the horizon. So, okay, I'll stop there. Thank you for your attention.
Okay. Okay, thank you very much. We've got questions now.
Hi, Sam. Thank you very much for the talk. Very nice. One question. You mentioned that the inflationary stochastic magnetogenesis models now will produce more magnetic fields on larger scales. So that would mean also that the deviation from non-Gaussianity, so the density fluctuation will be also stronger at larger scales, or?
Yes. Yeah. So that this effect on this matter power spectrum will be slightly different Yeah, and maybe on slightly, it'll still be small scales on the matter power spectrum, but there'll be some shift on exactly what scale or what scales are most affected. So yeah, so it's interesting that, to constrain whether that's tens of kiloparsecs or kiloparsecs, I don't actually know the numbers off the top.
Okay, thank you. And another question. Some models, I know, for example, that the group of Valencia, Vicente Quiles, etc., found that a lot of the gas that is actually in voids, but a large percentage come from very high density regions, even from clusters. So that could explain the fact that you are finding magnetic fields in voids, and not necessarily that is primordial.
Yes, so this is a key question for the whole field, and the simulators particularly, is how to get volume filling fields, that are produced in stars and galaxies into filling these cosmic voids. And so far, the most extreme scenarios are like that 30% of the voids can be filled with these fields from galaxies and stars. And so that's still not enough to explain the actual suppression of these gamma ray cascades at the moment. So yes, but I showed this 7 megaparsec radio galaxy. This is definitely not in the simulations. And so if you have radio jets, also many of these in the early universe filling these voids, maybe really astrophysical sources can fill these voids, but at the moment the evidence suggests no. But
okay, perfect. Thank you.
So, more questions? Nope. Okay.
So first of all, congratulations for the talk. It was very nice. My question is concerning instrumentation. So we will have SKA in a few years, but both sides are in the southern hemisphere, and I guess that gives us access just to half of the sky, so to say. Are there any plans for similar instruments in the northern hemisphere? And what's the future of LOFAR in that picture?
Great question. So most of astronomy has been biased, I guess, for quite a while to the northern hemisphere. But now, with the SKA and ESO and everything, the southern hemisphere is now getting, the newer and nicer instruments potentially. But so I think they're perfectly complementary to each other. We will have the SKA in the southern hemisphere, but we have LOFAR in the northern hemisphere at meter wavelengths, and this is currently going through an upgrade. So now we had the LOFAR 1, which I basically showed the data from, and we have LOFAR 2, which is about maybe twice as sensitive for the observations that I do. And then we also have this centimeter telescope called the Very Large Array, or the VLA, and this is also going through an upgrade to next generation VLA. So there are already plans for northern hemisphere telescopes to be advanced in the coming years that will remain competitive with the SKA. So even LOFAR at the moment is more competitive than the SKA will be for certain science cases, because LOFAR can make images at 0.3 arc-second resolution, whereas in the SKA, low at the moment can only make images, around a few arc-seconds. But it has much better sensitivity.
And just a follow-up question, maybe it's a little bit politic. If you see LOFAR stations, right, it gives the impression that if you would install another station in Spain, right, you would increase the aperture of the whole system. So since Spain is actually a full member of SKA, why aren't we involved in LOFAR?
Yeah,
I don't
no, it's a great question. So there are some efforts to try and include a LOFAR station in Spain. The advantage, is good for maybe the Spanish radio astronomy community. The scientific advantage is not huge in the sense that we have lots of the long baselines. What we're missing actually is some kind of intermediate scale baseline. So we have lots of telescopes in the Netherlands, and then we have lots kind of spread throughout Europe, but then we're kind of missing kind of intermediate things. From a scientific standpoint, most of the effort, kind of should be put into these intermediate distances. But it would be exciting, yes, to expand and to include telescopes in Spain. But also these 0.3 arc-second images are computationally very demanding to make at the moment. And so we're struggling to make all-sky surveys at this resolution because we just have too many pixels, and it takes hundreds of thousands of CPU hours to actually produce these images. But so it's of interest, but it's kind of progressing slowly, so it's not sure. But it's cheap, so relatively cheap. So it's of order like €1 million or so to put one of these LOFAR 2 stations somewhere. So it's definitely doable.
Okay, thank you.
So, any other question? No? Okay, before we say thank you again, I would like to remind you that it would be great if you were proposing speakers, okay, for the colloquium. All the slots in the year 25 are open, so please let me know if you got any suggestion. Anyway, thank you very much for such a nice talk.